Good morning. My name is Ayana Ghosh, and it's a pleasure to be here today. Thank you for the kind invitation. Before I get started with the research that I do, and I do not do gravitational wave astronomy, but I do a little bit of AI and machine learning in material science. So I wanted to share a bit of brief background because I'm very new to the campus. So I was across the Atlantic for a little while, starting from my bachelor's all the way, getting PhD, postdoc, and becoming a staff scientist at Oak Ridge National Laboratory. And then very recently, it's not been even 2 weeks, I joined the department here, the physics department, as an assistant professor. So if you are going to be interested in some of the things that I'm going to talk about today, please get in touch, stop by, say hi, whenever you want, and maybe some career trajectories also we can decide. All right. Now, in terms of the research areas, mostly I am coming from the condensed matter and materials physics background. So I look into evaluating different type of material properties across various landscape in terms of perovskite oxides, 2D materials, heterostructures, and so on. And mostly I do theory and computation. So my tools are my first principle simulations and then developing and implementing AI and machine learning methods. In terms of the first principle simulations, we would do density functional theory within different approximations, ab initio molecular dynamics, and some phenomenological models. And then going all the way in terms of the computational methods for AI and machine learning, from the statistical models like random forest, decision trees, to Bayesian optimization, some of the neural nets. But very recently and very interestingly, which is something, some of the examples that I'm going to be focusing on, is how do we integrate causality and causal models into this AI, and why do we even need so? But in general, the overall objective of my research is to really understand some of these material physics puzzles, but then also develop this comprehensive understanding where we can build in the nuances from both theory and experiments together, which has not been done yet, which has not been achieved yet in a lot of senses. Now, on a given day, as a scientist, let's say I wake up and I want to think about this question. Maybe there is a structural distortion that causes a property, something called ferroelectricity. As a computational person, as a theory person, what would I do? I would go and try to make this crystal structure. I would run or perform some computational simulations that would give me an estimation on the geometry and properties. And then hopefully there is an experimental colleague that I can call up and say, oh, can this material be synthesized or characterized? And then this person is probably going to tell me, oh no, there is some defects in the system. You have to figure this out in your calculations. And there would be a feedback from this experimental colleagues. And that would help me and him or her to get this comprehensive structure property relationship understanding of this material or this question that I want to understand in. So largely, if you take this as an example, but think about this for the physical sciences, the conventional way to think about problem is very much physical intuition or hypothesis driven. That's how we solve our physical science problems. But in the past decade, we know that AI machine learning models have surged everywhere, and they come with awesome data processing powers, which enable them to do data-driven pattern recognition. And you can pick and choose your favorite algorithms and models. And largely, they are very good at drawing correlation-based insights. They are getting very, very good in prediction accuracies. Finding needle in a haystack. So if you have a large enough data set, how do you sort of make a subset of it, or maybe turning and narrowing down your compositional search to something that would get you the targeted functionality or property of interest? So these are all the things that are these models all these generation models that they have that they can do really well. But as a scientist, I ask this question: how do I actually learn the underlying physical mechanism? Where am I learning anything physics? And the question that we pose in our research is, it is not only this data-driven pattern recognition type of models that would be able to do it, but we have to integrate some sort of a structured reasoning in the form of causal reasoning or logical reasoning, in some way building the intelligence into the models that would not only give us the structure property relationships from this correlation-based insights, but also help us understand the underlying cause-effect relationships that govern a physical or chemical phenomena. How do we do it? There is no rule book. So this is where the research comes in. But before I get into the details a little bit, let's look up some sort of a workflow where you have an AI machine learning guided, machine learning, some problem that you want to look at. So you would start from a data set, and that data set can be from simulations or experiment. And then there is the forward design. You already know that you're going to train a model, and then you get some prediction. And then there might be some other model that you have already access to, which was trained before, and that could help you to do some inverse design. What we are proposing is this, that we are going to integrate, and if we're able to do so, and we do have some really cool results in the last few years, be able to build this type of graphical causal models that delineate the underlying cause-effect relationships and also give us the mathematical formulations. Of course, these come with their own set of assumptions, and we need to check their validations and so on. But if we are able to do this, and then integrate that within the pipeline, we're not only relying on doing this forward and inverse design based on the data-driven heuristics, but also be able to integrate these cause-effect relationships that carry the physics or the physical laws in it. Maybe great for design, maybe actually would be needed for discovery, where we actually want to tap in something that doesn't exist. So a material maybe that does not exist at all, how do I find a new structural motif that can host some sort of skyrmion lattices or so on? Okay, now very naive way to think about it. And this is nothing to do with mathematics or physics, but day-to-day life maybe. So on a given day, my productivity largely depends on these two factors. If I had coffee in the morning, and then if I have internet. You give me these two, I get started. But then for me to able to have coffee in the morning, I had to get up in the morning. I had to have enough sleep. My sleep is dependent on many factors. What was the weather? If I had worked out, what did I have for dinner? Of course, how much time I spent on Insta. And then maybe some meetings I got into, maybe a fight with my mother, all these things. But if you keep on collecting this data over months and years, and then just do some sort of a data-driven machine learning model, you're gonna probably end up being, oh, this is sort of the coffee feature is the most important. So you're basically ignoring all other possibilities that can get to your productivity that contribute. So you do not have much understanding on the underlying process, how the data was generated. So this is the question that we are trying to answer. How do we do this? So this is a very quick intro, and I wouldn't have enough time at all to go into details, but there are a bunch of tutorials and stuff, and maybe I will have the opportunity to do some sessions later on. But in terms of the graphical causal models, there are primarily three types: common cause model, causal chain model, and common effect model. So the common cause model, in which you have this single cause that influences two effects; causal chain model, in which you have an initial cause that affects Y, and then you have its effect on the final, that's Z. And then the common effect model, where you have two cases sort of independently affect your Z. And the task that we are trying to achieve here is this, and this is sort of the decision ladder, where you have to make the decision on the association. So that is almost like correlation and what you have already the data on. And that is what the most machine learning models of today's age are doing. But we have to get into the interventional, where we can also estimate what if something changes in the data and what is going to be responsible factor behind that. And then estimating the counterfactual scenarios, which is much more difficult, where you have no data whatsoever. So if you want to make a really good decision, you have to be able to tap into these ladders, which is not something we are able to do at the moment. We are mostly, doing this associational thing. Now, a little bit more on the causal studies. So you have to just take my word for it for now, because again, I'm not going to get into the math here, but you're also welcome to check out the tutorial. So in general, these models build on the concepts and techniques of the statistical modeling, but they also sort of operate at a more advanced level than statistical information. So it's not just Bayesian network, but you have multiple assumptions to make sure that those are the real cause-effect relationships we are seeing. And of course, it's not an easy task. But these studies can be largely divided into two: the causal inference and the causal discovery. The inference part is sort of a little bit easier, where you are sort of estimating the effect of an intervention, of a change or a treatment. Therefore, you're assuming the causal relations are already known. And the discovery part, which is always very difficult, where you really do not know the underlying cause-effect relations and you want to discover it without any predefined assumptions. Now, I'm going to show you how some of the things can be done integrated in the materials. Yeah, go ahead. Sorry.
On the previous slide, in the causal inference models,
yes,
is it necessary to know the nature of the causal relationship, or the fact that there is a causal relationship is enough?
I think nature of the relationship also matters, because
you know precisely the nature.
Yes, yeah.
And otherwise there will be degeneracies, right? I mean, there could be different relationships
right.
related to the same.
Exactly. So we have to come up with identify the unique relations, and yes, yeah. Now I'm going to give you examples on the things that we have already built on this, but again, I know the audience I'm speaking to is interested in this, so I was like, okay, when I go through the slides, the examples will be on materials, but maybe you will see that the computational methods could also be useful for your problems. Particularly, I think, separating some sort of noise versus instrumental artifacts, understanding outliers and rare events, reconstructing some of the dynamics laws, sensitivity or analysis pipelines, and modeling uncertainty. So just keep these maybe in mind, pointer, and potentially after the talk or so, we will be able to find some synergies, in terms of what we do versus what you are more interested in. All right. For the materials, one of the classes of materials that I have been working on is ferroelectrics, particularly these hybrid improper ferroelectric materials, because they have direct applications in the technological devices. And largely, of course, the idea is, how do I design this new hybrid improper ferroelectric materials? And typically, a design challenge these days for any type of material scientist or a computational physicist is, okay, I have a AbO3 type perovskite. I go and choose all the compositions that are possible. I do a high throughput computations and then get to like 10 possibilities, and then maybe happy with it, and publish a paper, be famous, and that nothing gets to the experimentalist part. But here it's a problem. Why? Because if I want to design an HIF, let's say in the form of double perovskites and superlattices, I actually need to ensure that these materials are in this specific structural arrangement, because this structural arrangement will only enable the exhibition of polarization, the ferroelectric polarization. So in order to do this design challenge, I actually need to understand the mechanism, understanding the cause-effect relationship that govern this formation of A-side cation ordering. Once I understand that, then only I get to design this. So similarly, maybe I'm also interested in reconstructing the entire energy landscape. That would give me the understanding of all the phase transitions that are possible from the high symmetry to the low symmetry phases. So how do I do this, and then also find the specific mode coupling that would drive this type of phase transition. And then For the ferroelectric material, switching is very important, that this polarization vector needs to be like up and down and so. So what is the mechanism behind switching that we can access experimentally as well, and try to understand some of this. So this is where we got started with this causal models, and this is actually the first time anybody has done this across the globe, where we looked into the standalone causal models, and these were the linear acyclic Gaussian models, and that was integrated with some of the decision tree type models to figure out these cause-effect relationships behind the formation of this specific structural arrangement, and then coming up with a mathematical formulation to predict the energy of formation for the clear layered ordering. And next, we also looked into how to efficiently do this energy landscape modeling. So we built actually sort of a representation, we call it the structural mode fingerprint, because essentially computing phonons with density functional theory is very expensive. So coming up with some sort of a fingerprint representation and making sort of a huge matrix representation, and then feeding that into the causal models to not only come up with this prediction on energy and polarization, magnetization, but also be able to reconstruct this type of energy landscape in a few seconds or 2 minutes, depending on how many materials in the data set that you have. And typically in the conventional way, if you have to reproduce that energy landscape, you're running hundreds of DFT computations that are expensive for even one material, so it would take you hours. And then, because we have these causal models, that also give us sort of new understanding or new mechanisms of physics that we can start to play with. In terms of the switching mechanism, we also, went ahead, did the computations, and figured out some of these materials that can have a high polarization and low switching barrier. And doing so, we ran into the second problem, or another problem, which is how do we tune this barrier, because there is a lot of different materials that cannot be accessed experimentally because the switching barrier is high. So it has to climb through this thing. So if it is too high, then this material, even if it has a high polarization, it cannot be synthesized experimentally, and it doesn't give you the polarization. And this is really fresh off the oven because it was just published recently, where I had built this causal reasoning framework that can enable controlling this polarization switching. So what happens is we build this causal discovery models, and then we integrate the causal intervention part, but there we are also integrating the physical constraints that allow us to change these variables in a physical way without destroying the entire crystal structure. And then we go back and do the validation with the simulations to figure out, what are sort of the experimental parameters or the drivers that we can also fold into our theoretical calculations to achieve this lower switching barrier. So for every single material we had in data set, and there was like 500 compounds, we now can have a precise prescription what type of physics can help to tune this barrier height, and how would you be able to synthesize that experimentally. So what is the substrate that you want to grow this material on, and what are the strains that you have access to intrinsically, and so on. So these are all the things you wouldn't be able to do at all without having some sort of causal reasoning. Next, we are expanding this into two-dimensional materials, particularly where you have the couple spin lattice symmetry interactions at the interfaces on the heterostructures, and you can also come up with different building blocks. And once you start to build heterostructures where you have materials that can be maybe an oxide versus a 2D material, then you are looking into an infinite possibility of your compositional space. So it cannot really be solved with your conventional AI machine learning methods. So we are working on developing these representations and models that can allow to do so, and come up with this new physics. Yeah.
How do you represent large N systems like this, where the atomic cause might be identical? Is there a recursive way of doing this?
Yeah. So let's say you have, so let's just take this example. Okay, so you have two-dimensional materials and you're trying to maybe put two-dimensional materials together, and maybe of the similar crystal structure, just the compositional differences. So in a way, your representation, so it's like an embedding that you want to feed in, that should represent the difference between, let's say, the atomic counts or the electronic counts and things like that. So the representation needs to be such that it actually has that type of information embedded in it. And then once you feed that into the causal models, then you can actually distinguish between what type of effect or what type of cause is coming from one building block versus the other, and what can happen at the interfaces.
Can there be some sort of scale-free models where one realizes that if you have a sheet as big as this of two different materials versus two sheets that are, say, 10 to the power 3 times as big?
Yeah.
The phenomenological behavior will be identical.
Right. So actually we have done this where we started from like unit cell monolayer system for 2D. I'm going to show you a picture of this. And then we wanted to just look into some magnetism and things like that. And then very naively and constructed this model. But because there is this embedding stuff built into it, we can also build in some uncertainty maps that can point us to the regions where we are not sure about the magnetic ordering. And then we go on to actually building a larger supercells to do the calculations. So even if this cause-effect relationships sort of was done on the monolayer unit cell level, we would be able to go and sort of extend that into a supercell level. The structural mode fingerprint that I talked about on oxides can also be able to do it. Largely, this is also because these are periodically boundary conditions enabled systems. Now the question is if you have defects. Okay, I don't know that answer yet. So but that's something I'm thinking about. Because once you have defects, then things may not be periodic, and then whatever you have built in your equivariance and all that would just fall apart. So for now, it works. Now, in a way that I mentioned about some domain agnostic things. Sorry. Oh, 5 minutes. Okay. Sorry, I'll have to just sort of go through this a little quicker. Now, although I was talking about like more solid state, there's also large things that I work on the organic counterparts like crystals and polymers and things like that. But this problem also still exists, that maybe in your problem, that you might have some sort of understanding of the underlying relationships for a smaller subset of data, and then how do you extend that to the bigger data set? And this can also be similar to this unit cell to supercell problem. And this is where we developed this active causal learning based on a graph similarity matrix and sort of this active learning process where we start from like a randomly sampled subset data set, and we can approximate this causal map in an iterative fashion and get an understanding of what it would look like for a huge or bigger chemical space, sort of building this global things. And we're also looking, of course, going towards more representation learning, sort of feeding in more different types of representations. So it could be one on some hot vectors, some symmetry versus electronic fingerprints to do magnetism. This is another part I wanted to sort of touch base, is also this Bayesian approach where you would typically use the Gaussian process as a surrogate model, but there is no physics in it. And how can we make that physics informed? So augmenting the Gaussian process, and then you can also attach some sort of a reward-driven acquisition function where you would be able to evaluate some hypothesis that would be great to reconstruct the physics. And I wouldn't have much time to talk about this, I guess, in terms of connecting to experiments, but there is a large work that I have been doing in terms of, going from, let's say, microscopy, or it could be some other characterization method, and then that estimates some sort of functionalities, but what is really the role of theory and computations here? Because how long does it take for, to generate a microscopic image few fraction of seconds versus how long would it take me to simulate 1,000 atoms? Still not there yet. So these are sort of the problems that we are looking into. We have developed some of the architectures that were implemented on the fly for the experimentalists, and then also looking into like regions of interest based sampling methods to have this real-time gap, but it's not there yet. So we're also looking into some surrogate models to go from images to spectra, which is another big problem here. And one other very important thing is this human AI thing. Where
anyone have a question? You
have a long question.
Okay, I have a short question. Oh, you have a question.
So, thank you for a nice talk. I have a quick naive clarification. For example, you said that you are integrating DFT plus AI/ML. So, when you say that, that means that you use the density function theory and then you design models to solve that density function theory?
No. So right now we are not solving the quantum equations with AI machine learning. Integrating DFT simulations I meant is some of the data sets that were built with DFT simulations data.
So based upon that simulation data, you are constructing these graphs, which is like
yes.
Okay.
Yes.
So do you also plan to do such kind of things where we use whatever the Hamiltonian is and you solve those equations in real time so that you make those graphs?
Yes. So I didn't have a lot of details, but so we already have started doing this with phenomenological model, particularly Landau models, where we were able to reconstruct and figure out some of the order parameters and the mode coupling things. That's what I was hinting at. So the next step definitely would be, integrating this step of going into probably constructing an effective Hamiltonian from the data with the AI ML. Another part to think about here is that would also sort of integrate or try to integrate the time scale and the length scale problem, right? Because how do I, let's say, think about electronic behavior at the quantum mechanical scale, and then maybe I understand ferroelectric polarization. How do I get that and then put that into the phenomenological model, and then maybe construct an LLG, and then go get into the device and things like that. So those are also the problems that I'm interested in.
So the application that I was thinking with respect to that was neutron star equational state. To solve effective field theory equations, and that solution is non-asymptotic.
Yes.
So those type of problems can be solved.
Yeah, so actually very recently I was working, I've an intern at Oak Ridge, and he's joined from Imperial, and he's very enthusiastic, and I was like, okay, we're gonna do equation of state. So, for all the systems, because for solids, there are so many equation of state. So how do you come up with, for one material specific question, how do you actually answer which equation of state is going to give you the optimized solution? And it doesn't exist yet. Right. So we have already started, yes. So we can surely talk about that into that directions, yes.
So I noticed that most of the systems you study are quantized in some sense.
Yes.
But I have a continuum question. So how do I think about causal models in situations, let's say a very simplistic situation, I have a rigid wall, a spring, and a ball connected with the spring. How do I represent this system under Newton's law?
Yes, yeah. So this is this is if I could show you my Google Colab stuff that I'm building. So this is one of the things where if I can reproduce a Newtonian equations of motion and things like that. And the way I'm thinking is maybe we have different case scenarios. Let's say, okay, I just assume that there would be no damping factor, and then I just write down Simplest, yes.
Class 10.
Exactly, yes. And then add maybe a damping factor. Maybe that damping factor has a very naive functional form, versus then we start to integrate some nonlinearity. All of this. And then feeding that into the causal models to see if we are able to, get this relations straightened out. And one other thing is this, that some of the causal models that we are working on actually build these mathematical equations first, right, to solve these relations. So if we can extract that and with some nonlinearity added, maybe we could do it. So we are working on it.
Do we need to know the equations?
No.
The solutions?
No. If we already know the Newtonian equation of motion, then there is no point to do it, right? So the assumption is like, okay, maybe I'm building sort of a model like a toy problem, right? Where there is just multiple different data that I have generated, simulated. It could also be collected from somewhere. And from that data, if I'm able to derive the equations. So that's, no. So you should not have a feeling.
You're trying to create Newton. That's what it is, right? It should come up, AI should come up with Newton's law and say this is the law.
Yeah, so the physical laws is not, so, okay, let me, okay.
Simpler question. Suppose
Yeah.
we knew the equations.
Yes.
How would I represent that system?
So then, if you already knew, then you could essentially,
Equations, not just functions.
yeah. So if you already knew the equations, then you could potentially just generate the data based on that, and then basically build like standalone causal models to see if it follows that. If the cause-effect relationships follow your equational form that you already had, because these cause-effect relationships stand on the mathematical formulations. It's like, some sort of this plus some epsilon factor, right? And then you would be able to match it up, right?
But
Exactly.
that would be like a normal least square sort of fitting, right? You just,
Yes,
it is
yeah.
not really machine learning at
Right,
that point.
yeah.
You know the law of physics.
Yes,
then
yeah.
You will just predict starting from the initial conditions, which will have some randomness, and then evolve them, and then
Correct.
see the aim with that
Yeah.
Right.
observations.
Yeah.
So I'm not thinking of doing this.
Yeah.
I'm trying to understand
Yes.
how to represent
Yeah,
this
so,
in Cosmos.
right. And so one other example I'm going to give, so this intervention causal reasoning work that I just talked about that, just was published. So there was an interesting observation that came out of it. It was very new physics, that from the Landau theory, what we knew that it would happen, it actually gave us some different answer, and it actually took me like 4 or 5 months, because I was like, I'm surely doing something wrong, but it's not. So that actually, so this is probably the next paper I'm going to write, is like reformulating the equations and so on. So it is actually going into the new physics that I had no idea about. And that's the entire point, that I want to discover. I just don't want to relearn the things, reconstruct the things I already know about.
I think the most important reason for doing this would be when multiple physical laws have to be combined together, that human brain finds it very difficult, because you have this law. But when it is in the machine learning, in the hyperparameter space, it is doing something which can be far more complicated than what human
Correct.
brains can.
Yes.
Or somewhere in the middle where you know the form of the law, but not exactly.
Right, yeah.
Some ideas you can give, like that will be like some physics informed.
Yes,
Sort of.
yes, correct. Yes.
Okay.
And that's where that hypothesis-driven thing is also coming up, where if you have multiple, we can come up with even multiple equations and then try to evaluate also with the causal part embedded in that. And it doesn't exist yet, so yeah.
Yeah, that will be like that previous talk, like in dimensions. Like you go to this dimension where one law is applicable, and then try to merge everything together
Right.
in a combined,
Yes.
like multi-dimensional problem.
Yes, yeah.
Okay, these interventions are very interesting, but we are really getting late and Chandra will be panicking.
But we might have a panel, a short panel discussion.
That's
so
also
we can
there.
come back to.
Yeah. Okay, so let's thank the speaker now. And then